So let's look at heat pumps, but first let's step back for just a moment and look at what we've deduced for a heat engine. For a heat engine, we've put heat into the system by virtue of the combustion of gasoline. We can also inject high temperature steam, but coming out of that heat engine is Q out. So heat went in at high temperature and heat came out at low temperature. But what also came out was work. Work out. And we know exactly how to calculate that because we did it when we calculated the efficiency of the Carnot cycle. Remember, we added up the work along each one of those legs, an isotherm, an adiabatic leg, another isothermal trajectory, and finally an adiabatic trajectory, and we can calculate the heat in because the heat in is exactly equal to minus the work along path 1. All right, so we reminded ourselves about the heat engine. Now let's look at a heat pump, because a refrigerator is a perfect example of what a heat pump is. We're going to see we can apply this to heating our house or our building in just a moment, but the principle is basically identical, and that is we are generating the flow of heat out, and in the case of your refrigerator, this is simply a process by which the mechanism, the mechanical part, is extracting heat from inside the refrigerator, so it's cold, and dumping it into the room outside. And the difference between those two is what keeps the temperature cold inside. The way we do that is that we put work in. So work isn't produced, work is put into the system to pump heat from the low temperature cold side to the warm side. But you can immediately see that if I have a house, which we're going to look at in just a moment, now let's suppose it's a cold day outside. Let's suppose we have 273 Kelvin air outside, but inside we want that temperature to be 293 Kelvin. That's plus 20 degrees Celsius. That's a very comfortable temperature. Now it turns out that if we analyze the efficiency of that heat pump, we call that the coefficient of performance, the COP. But if we go through exactly the same logic that we applied to the Carnot cycle, that coefficient of performance is equal to T hot divided by the difference between T hot and T cold. Now I can put in my temperatures, my coefficient of performance. This is the maximum theoretical coefficient of performance that's available. So T hot, that's equal to 293. And my difference, T hot minus T cold, is 20 Kelvin. Now that's a factor of 15. But that says something very profound. That says 1 unit of work done converts to 15 units of heat inside the house. Well, it turns out that that's the theoretical maximum, but in practice, the coefficient of performance of heat pumps now, so I'm going to say this is actual, is about equal to 5. It's been increasing, but that means that 1 kilowatt hour of energy put into a heat pump generates 5 kilowatt hours of net heat into the house. So let's calculate what that means. Let's assume we're still generating electricity with fossil fuels. Now, of course, when we go to renewables, then the renewables deliver 100% of the power we're talking about. But let's assume we've got a natural gas burning power plant and we put in 100 units of chemical energy. And if that power plant is 50% efficient, it means we're generating 50 units of electrical power. Now, when we transfer that power to the house, we're going to lose somewhere between 1 and 5%. Let's say we lose 4%. That means we have 48 units of electrical power delivered to the house. So now I multiply this by this factor of 5, which is the coefficient of performance, and I come out with 240 units of heat added to the house. Now, let's contrast that with a case where I'm burning natural gas in the basement in my furnace. So I have my house here, but now I've got a flame heating the house through natural gas, and a natural gas furnace is about 90% efficient. So that means I have 90 units by burning natural gas in my basement. But I've got 240 units by burning the natural gas in a power plant using a heat pump, and that gives me a huge gain. In fact, I can calculate that 240 units of energy from the heat pump divided by 90 units of energy from the natural gas furnace. That gives me a factor of 2.7 gain. Even if I'm burning the same amount of natural gas in the power plant as I'm burning in my basement. This is an example of how important heat pumps are, because they can deliver heat to houses, to buildings, to factories with this huge gain. But more than that, when you invest in a heat pump, it means you can drive it with electricity. So as the system becomes more and more dependent on renewable energy, wind, solar, geothermal, you can use exactly the same system, but the gain is tremendous. So we finish up then by reminding ourselves of two very important factors, and that is, if we look at the estimated energy consumption, and we're picking the United States as an example here with the Lawrence Livermore National Laboratory diagram, and as we looked at before, we're looking at the insertion of primary energy on the left-hand side, and we're tracking that primary energy: petroleum, coal, natural gas, solar, hydro, wind, and so on. 80% of that primary energy is fossil fuel based, but we just calculated the efficiency of a heat engine, and the efficiency of a heat engine is very low, and that's the reason that 68% of that primary energy is wasted. Only 32% is useful. That describes immediately how poor a heat engine is in converting chemical energy to useful work. But now let's look at one other aspect. We used 100 or so quadrillion BTUs of energy a year in the United States. If we could eliminate this 68% waste, that means that the total energy that would be required to achieve exactly the same standard of living would be a fraction of that. It would be, let's say, 40 quads. And we already know that electric automobiles are extremely efficient, enjoyable to drive, have better performance than a gasoline automobile, but we've just demonstrated that a heat pump depends on thermodynamics, and that heat pump is extremely efficient. In fact, it produces more heat into the house than the electrical power provided to that house. And you step back and you say, how can that possibly be? The reason the heat pump is so effective is that nature is based on 0 Kelvin. So when we look outside and it's freezing 273 Kelvin, and we want our room inside to be 293 Kelvin, that means we only have to put a tiny amount of work in to raise that energy from 273 to 293, the energy contained in the thermal energy of the air. That's why a heat pump is so profoundly powerful in heating buildings, homes, and so on. It only requires a tiny amount of work to elevate from 273 to 293 Kelvin. So now let's look what happens when we convert the entire system to electricity. So the first thing we notice is that we consume not 100 or so quads, but something on the order of 40, 42 quads, because all of these systems, the heat pumps, the light-emitting diodes for lighting, electric automobiles, all operate off of electricity. So we have maybe 10% that's wasted, we have 90% that's useful to do whatever we wish: run factories, run machines, heat, cool, whatever we wish. It's all electrified. The only element of that flow of energy that we need liquid fuels for are aircraft. But it turns out that biomass is more than capable of supplying all of the liquid fuel needed for all aircraft internationally. And so this is the picture of the future. And this picture, in which the electrical output is 96% of all, driven by solar, by wind, by geothermal, by nuclear, by hydro, by biomass, and so on. All of those forms of renewable energy produce electricity. And every single thermodynamic device that we've worked so carefully through uses electricity. And you can see how the heat engine may have started the Industrial Revolution, but heat pumps, electric motors, light emitting diodes,